So, more on sensor networks. This is I had a really fun time, thank you Andrew and the committee, just going through and thinking about the work we did 15 years ago or so and what was important about it. This was the slide that I actually started with at Census in 2004 in Baltimore. And show of hands, who was in Baltimore at Census? One, Ben Greenstein's here somewhere. There you go. Oh, yeah, put your hand up. So the good news is most of you haven't seen this, but I'll give you a little bit of an overview of the context for why did we do the work that we did. You'll notice we didn't actually title the paper BMAC. A lot of people refer to this as the BMAC paper, and I'll go into a little bit of why that is. So to set some context, Berkeley has these research retreats every 6 months, and we all get together in Tahoe or Santa Cruz, and we talk about the problems that we're facing, and we bring people in to provide advice. And on the second night of these research retreats, Chris Peaster would get up and he would make cocktails for everybody, and we'd do this kind of gong show style, crazy, wacky ideas thing. And Kameen Whitehouse and I got up and we said, you know, we have this idea. We want to put weather stations on the roof of every house. And then we could predict microclimate variations, and we could know a lot more about how weather patterns develop. And so this was 2002. If you recall, that was the first season of American Idol. So just Kelly Clarkson. And so we proposed this, and all of a sudden I get an email from Alan Mainwaring at Intel Research. And Alan had heard from David Culler, hey, you know, Joe's thinking about this weather station idea. And Alan says, you know, could you put an occupancy sensor on there to detect, you know, warm animals? And I was like, okay, hold on. There's a weather station on the roof of a building. I don't know why he wants an occupancy sensor, maybe for theft or whatever. He said, no, we want to study these birds. So now, imagine you're on an island off the coast of Maine. So this is Great Duck Island, and you're this individual here, kind of kneeling over, and what you're doing is you're putting your hand down a 6-foot burrow to see if there's a bird in there. And what you want to know is if the bird is there, then that's good, that's where they're nesting, and you record that season to season to make sure that this endangered seabird isn't being disrupted. And so we thought that was probably not the best way of doing this. Turns out birds don't like it when people put their hands down in their nests. And so our vision of the world was, of course, why don't we put some sensors down there? That'd be awesome. And so that's what we did. We embarked on a project with Alan where we took a bunch of sensors and we actually put them on stakes about 3 feet above the ground, and we formed a single hop transmit-only network. So think about that. It's basically, there's no way to communicate with the nodes. They could only communicate back. They barely duty cycled. They died after a few weeks. But they worked, and it kind of proved it out. And we said, we think we can do much better than that. And it kind of brought into focus what the problems really were. So we started with these things on the left, which were pretty big. This was the sensor we used in 2002 on Great Duck Island. And we built 2 new sensor platforms on the left that were much smaller, and we used them in 2003. And the thing was, we needed them to last for an entire breeding season, so we needed to duty cycle the radio. We needed low power operation. And we ran around Intel trying to get funding for this in Berkeley, and everybody told us we were crazy. They said, don't you understand the laws of physics? You know, RF doesn't work underground. It only works above ground. And we said, yeah, that's fine. That's what this multi-hop mesh networking thing is for. And they're like, I don't know about this. So we continued on with it. Basically in 2003, we deployed this network. It was over 50 nodes, and it lasted the entire breeding season of the Leach's storm petrel. But the question is, how did we get there? And so we started with a completely naive single hop network and ultimately moved to a network based on low power listening. And the reason we ended up doing this low power listening thing that's presented in this paper is that we tried all of the other synchronization protocols. And they either would get out of sync and they would then like go off on their own and consume all their power, or the code was really complicated and had bugs and we could never find them. And so we said, well, what if we just said, turn the radio on periodically, see if there's anything there. If there's something there, stay on and receive it, and if there's not, go back to sleep. And the difference here is that we wanted to shift the burden to the transmitters, make the transmitters spend energy sending the power when they have something important to say, and then the receivers can be very, very low duty cycle, and in contrast, when you're synchronized, you have to wake up for longer periods of time, even if there's nothing going on, so the receiver takes on that burden. Well, what happened was Jason Hill and I basically sat in front of an oscilloscope for days, measuring this current consumption curve of a ChipCon CC1000 radio. And it turns out that there's all these different states that the radio goes through. It's kind of a black box test, but we could tell when different data would become valid and what was the smallest amount of time you could keep a radio on such that you could detect if there was something on the channel. And so what came out of that is basically this unscheduled listening where you have two nodes that will just wake up on a periodic schedule, and if somebody wants to talk to them, they just blast them for a long period of time and say, hey, I know that you're going to be on every second, so if I send you a message that's over a second long, you're guaranteed to get it at some point. And that was really the crux behind low power listening. And so that's what people normally remember about this paper. Turns out low power listening, this wasn't the first time this was ever proposed. Aloha had low power listening. There was WiseMac and other approaches. But people remember it for that, and we called it BMAC. Berkeley Mac is kind of a joke. Haha, Berkeley, we named it after ourselves. Kind of like Berkeley Systems Distribution. And so what I wanted to talk about was what we really thought was the contribution at the time, and maybe still is, which is the way that people were building sensor networks is you would say, oh, I'm doing a bird monitoring application, so I'm going to build my bird monitoring network layer, my bird monitoring link layer, my bird monitoring radio if I need to do that. And I'm going to do a different application around perimeter protection. I would build my perimeter protection networking layer and so forth. And so it would be these big black box monolithic systems that wouldn't understand the needs of the layers above them. And what we said is, well, what if we just replaced the idea of the link protocol in there and instead allowed the layers to exchange control and cost information? If I know how costly it is to do this activity, then maybe I'll change my network behavior or think about other ways that I could route that packet. And similarly, if the application can tell me, hey, I'm not going to have anything for you for a few hours, you may be able to make better decisions about how you're going to use the radio and participate in the network. And then finally, the network knows what your neighbors are and who you're coordinating with. So the idea was just give a little bit of information back and forth, and we can actually make the system much more flexible and adaptable. The really neat thing about this approach is you can actually build all those other protocols on top of this interface. So we built SMAC, which was this slotted network protocol, network end-link protocol, actually, and we built it just directly on top of BMAC. And then we took bulk data transfer, so if I want to take my log of sensor data and just push it all out to the base station, well, why don't we do that in an efficient way as well? And then we measured the results of just building these on top of this abstraction. And what was really interesting, and there's a lot of lines, but at the end of it all, it basically performed just as well, if not better, than these more monolithic constructions. And so the bottom one, the bottom black line is the optimal, the black kind of X line is what we're able to do with BMAC, and then TMAC, which was the best at the time, was slightly above that. So you could implement these network protocols, and it turns out this was less code size, so it was easier to debug, easier to prove that it was correct, and it was also less RAM and memory size, so there was less buffering going on because you weren't trying to take care of multiple layers of reliability there. So it got me thinking about what were some of the other things we did with this paper and where did it end up. One of the things that was really interesting as I was writing the paper was thinking through the scientific method. Our field is computer science, science right in the name, and we often don't actually present our research in sort of a scientific method sort of way where we have a hypothesis, we have a set of tests. Ideally, when we test, we only change one variable at a time, not many variables at a time. And then we prove that by doing these changes, we actually get better results. And so credit to the SMAC folks, they actually defined a set of topologies, we extended some of them, and then we replicated their results in our paper on a completely different system, completely different set of hardware, and we were able to show that by changing and re-implementing SMAC in this other way, it could actually work as a better protocol than how it was originally designed. And it was just something that kind of struck me like, oh man, in computer science, we just need to think more about this sort of scientific method concept in our work. But there was a second thing that came out of this, which was probably even more impactful to me, that none of you would have ever known, which is I sent my paper off to Jason Hill. He had just graduated. Jason went off and worked on synchronized networks. He started Dust Networks. And when I got the first copy of my paper back, he had scanned in all the comments, and it basically looked something like this, where on every single paragraph, he wrote the words, "Why do I care?" And so I'll make that real big for you. It just kind of completely changed my mind and my approach to writing, and I think it's probably one of the things that I learned most as a graduate student was how to write and how to write in a way to communicate ideas, because even though the results may not be the best results in one paper or another, the important part is us conveying our ideas to the community. And so I still do this today when I'm writing papers or reports or even product specs or whatever. The whole point is, why do I care about all this? And so the thing I thought, so a couple other things. There's been, over the last 14 years, a bunch of work that's gone on since we've published this. Jonathan Hui, who I worked with at Berkeley, went off and has been part of the IEEE standards process, along with Wei Hong. In 802.15.4e, in 2013, they actually introduced coordinated sampled listening. The idea there is you wake up and the transmitter tells you when they're going to send their next packet to you, and then you go back to sleep and you wake up at that time. It's basically low power listening with just sending you sort of the time of the next wake up. So that went into 15.4e. It then also went into the 2015 edition of just regular 15.4. So all 15.4 radios will have this going forward. Zigbee RF for consumer electronics also has this since about 2008. And then there's a lot of vendors that are now supporting this in their chipsets, from TI to Atmel, the Freescale NXP consortium, and so forth. And you can find it in a bunch of the real-time operating systems, whether from the vendors themselves, like TI, or from TinyOS or Contiki or any of the number of research operating systems. So the thought that I wanted to leave you with is, I think a lot of the reason we do this is we want to build out this infrastructure and these principles in such a way that all kinds of other people can build on these concepts and build really interesting, impactful applications. And so this is a video that we took in 2003. I think we only showed this once, and maybe at Census in 2005. And it ultimately ended up getting shown more in ornithology conferences than it did in computer science conferences. And the reason is that this is the first video ever recorded of a Leach's storm petrel feeding a newborn chick. Because it happens underground and it's generally dark, there's not a good way of knowing what's going on there. And so what we did was we used the motes. They would signal that activity was going on. The motes would then trigger the camera to turn on, and through Wi-Fi we would send the camera signal back. So what's cool is it's not just that we contributed to the field of understanding in terms of mobile communication, but I think most of the papers, all the papers here, have also contributed to the field of understanding of science and also the applications that we can build. And I'll leave you with that. Thank you.